Okay. So now we know the load, we know the formula that we have to apply. The next thing we're going to do is we're going to do failure analysis. Did I start recording? I did. Okay. And I did mention before that we knew that this plane is where failure is going to occur, at that plane. Okay, I remember I did mention that to you all. Okay, so now we are going to look at it in a micro level. We're going to look closer what's going on. Okay, so I'm going to draw the cross section. So this is the cross section, and I'm going to draw our transformation. Y, that's our Z, and this is our rotation about X. Okay, then I'm going to place 4 elements. Okay, so we know, before I do that, I'll draw our center line. And I'm going to place 4 elements. Okay, I'm going to place 4 elements, and we're going to call this element A, element B, element C, and element D. Okay, you'll see element A, B, C, and D. Okay, and we're going to create a table. Okay, we're going to create a table. So as you can see over there is our element. I'll make this smaller a bit. Eugene, great. Okay. So we are going to have elements. Element A, element B, element C, and element D. What we are trying to do is we are trying to identify qualitative, not quantitatively, qualitatively. Qualitative means the likely, right? You don't see the values, but you know which element you should analyze. For now, we don't know. Okay, is it? We know that plane will fail, right? At that plane, it will fail. That's the most critical part. But is it at A, the failure will start first, or is it at element B, element C, or element D? And we did something very similar in the previous example. Okay, so we're going to do this now. The previous example does not have axial loading. Now we have. So if you look at, we're going to create a table, and we're going to use stress X is equal to minus P over A. Okay. So we are looking at the 2,500 over here, and all of them are going to observe minus P over A, all of them. Okay, they're all going to see the minus P over A. Okay. Then the next thing that we're going to look at, we are going to look at stress X is equal to minus, or is equal to mz over izz multiplied by y. Okay. And if we look at moment about z, right, using right hand rule, is coming down this way. Okay. That is our moment about z, and we know That's the advantage of using what I've just taught you, okay? MZ, the head will be compression, right? The tail end will be tensile. You don't need to worry about the formula, you know. So when you look at element A, it will be positive MZY over IZZ, right? At B is at the centroid, so it's negative, right? At C will be minus MZY over IZZ, right? Because it's in the compression. At D will be at 0. So from here, due to normal stresses, right, we can ignore, we know it's definitely not B and not element D, right? And if you look at magnitude, this will have the what? Maximum compression, right? This element A have compression and axial loading, and in bending is what? Tensile. So it will not have the maximum what? Amplitude. Okay. Then we go further. We look at shear is equal to TR over J. And all of them are going to see what? TR over J. Because all of them are going to be at the what? At the radius. Element A is on the radius. Element B is on the maximum radius. Element C is on the maximum radius. Element D is on the maximum radius. So it still stands that element C is the one we have looked for. Now I'm going to go further. What if now, right, we have, I mean, this problem we don't have. I'm going to change the color. Right. Let's say if now we have a Vy. Right? What if we have a Vy? So we know the shear is equal to Vy over Izz Qz divided by T, right? So we know if we have a Vy, element A will be equal to 0, element C will be 0, whereas the other two we will have Vy Qz over Izz T for element B, and element D we have Vy Qz over Izz T. Okay. And then if we were to have the value of the shear, okay, and shear is equal to, now I'll use a different color now. Let's say if we have the value, the shear will be in Vz over Iyy Qy divided by T, right? So this is our what? This is our Vz. But for our problem, for this case, we don't have, okay? So I'm just saying if let's say you're having Vz and Vy, Vy and Vz, what must you do, okay? So at element A, you will have Vz Qy over Izzt. At element, that's at element A. At element B will be 0. At element C, you have Vz Qy over Izz multiplied by T, and this is equal to 0. Okay. For our case, we don't have Vy. Okay, Vy we don't know. Okay, we don't have. Or for this case, Vy is equal to 0.
Excuse me, Eugene.
Yes.
Is it IZZ or IYY for the VZQY?
Vz is Iyy. Vy is over Izz is correct.
Okay.
Okay. So we know that Vy, we know that Vy is equal to 0 because we are not given the value. We also know that Vz is equal to 0. We are not given the value. Okay. So from here, we know the element to select due to normal stress is this. So we are going to analyze element C. Does that make sense? Yes or no? Right? Why? Because the axial load is in compression. The bending moment is in what? Compression. We did not pick element BA is because the axial load is compression, but the bending is what? It's in tension. It will not show the maximum magnitude in terms of normal stress. Okay, so from here, we are going to element C. Okay, element C has the highest magnitude in normal compression or compressive stress. Okay, so therefore, it is used or it is selected for analysis. Okay. Okay, so let's now sketch our element. Okay, what's the next one? Okay, so we know we are going to apply Tresca. Okay, and we know Tresca criteria has two forms, right? We know that the first form is maximum stress is equal to half stress max, right? Or are we going to use stress max or shear max is equal to half stress max minus by stress mean? Okay. So which one are you going to use? The first form or the second form? The only way to do this is to construct the only way, okay, the only way to and to find out which formula to use is to sketch 3D mold circle. Okay. You don't need to draw it, you need to sketch. Okay, so here we go. Okay, so if we were to now, okay, now we're going to view this element. Okay, I'm going to I might give you a headache. Okay, so now I'm going to take the image of the shaft again. I'm going to give myself a headache also. So now I'm going to draw. Let me have some. I'm going to draw X in this orientation. I'm going to see Z over here, and I'm going to do Y. Right, you see what I'm doing, right? Right, I'm going to rotate the shaft by 90 degrees. If you look into the page, or look at the page, I'm going to rotate it anti-clockwise by 90 degrees. Okay, so element C is definitely down here. Element C is down here. Right? So when I rotate it, I will see this. Okay. So the shear stress will look like this. Because the torque is rotating this way, so you follow the torque direction. This is torque, the x direction, right? Then we what do we have after that? So we know that we have a stress x expression. Okay. So this will be this plane. Okay, so this plane, this shear will be the intersecting plane. So shear x z. Okay. So this is shear zx. So what we see is our stress z is equal to